KPA has been conducting these talks or lectures since October 2023, almost every Sunday, on a variety of topics, all the way from quarks to cosmology, so that our members or students can benefit uh, from various speakers from colleges, universities, and institutes on topics that might not be very familiar with them. So this is a kind of an outreach activity that we are doing, and we have been very successful, I must say, with the cooperation of the faculty from colleges, universities, and institutes.
Hey, good morning, Lydia.
And today we are having a who is the person here? Please don't.
Question.
Who is this? So today we are having a very distinguished astrophysicist, Professor Bala Iyer. He is going to talk to us about gravitational waves and how they form a new window. They can be used as a new window to study the universe. And I might also tell you that we have been conducting these talks in Canada also, with the view of encouraging the usage of Kannada in higher education. Because the reason being, as you know, most of the students and even teachers find it very difficult to communicate, and it's very natural that since we are not native speakers of English, that we'll be having difficulties. So, in order to encourage this transition or efficient communication of knowledge, so I think ultimately we have to switch over to our own languages, Indian languages. But when that happens, we don't know, but we should make an attempt. So we have been doing that also, and we are encouraging the talks in Kannada also. So today's talk will be delivered by Professor Bala Iyer. He will speak for 50 minutes, followed by 10 minutes of question answers. So before I request him to give his talk, I'll just give you a brief introduction to his career. Most of you might be already knowing about him. So Bala Iyer is currently ICTS Endowed Visiting Professor at ICTS TIFR Bangalore, and he's a co-principal investigator of the LIGO India Scientific Collaboration. He completed his BSc, MSc, and PhD from Bombay University. He was in the Raman Research Institute as a faculty during 1982 to 2014, and worked earlier on astrophysical applications of general relativity, perturbation methods, and black holes. Since 1990, he has worked on calculations of gravitational waves from inspiraling binaries of neutron stars and black holes. He is a fellow of the American Physical Society and the International Society on General Relativity and Gravitation. He has been chair of the Indigo Consortium from its inception in 2009, and was the principal investigator of Indigo participation in the LIGO scientific collaboration during 2014 to 19. He was a member of the core team for LIGO India mega project proposal. He is the chief editor and subject editor on gravitational waves for the online journal Living Reviews in Relativity, published by Springer. So Bala Iyer has been a visiting scientist in France, UK, Germany, and USA. He has been involved in the REAP, Research Education Advancement Program for BSc students at Bangalore Planetarium for over 2 decades, and has been involved in so many public outreach activities on general relativity and gravitational waves. So with this brief introduction, I now request Professor Bala Iyer to present his talk. Over to you, Professor.
Thank you, Basavaraj. So let me begin by thanking Basavaraj and the Karnataka Physics Association for this invitation to talk on gravitational waves on this Sunday. My plan is the following. I begin with a primer on gravitational waves, then talk about the discoveries and breakthroughs which happened in the first and second observational runs, how in the third observational run the research has been consolidated, what is the current status, and what are the future prospects for this particular subject. I may not be able to go till the end, in which case I'll stop where I reach and then leave the rest to the questions.
No problem, no problem.
The story begins with Einstein's relativistic theory of gravity. As everybody knows, this theory is supposed to be an epitome of mathematical elegance, conceptual depth, but importantly, observational success. Every time you test this particular theory, whatever Einstein's theory predicts comes out to be matching with the experiment. In Einstein's view, gravitation is synonymous with space-time geometry and mathematically described by the curvature or distortion of space-time. Einstein's equations are a system of rich 10 nonlinear partial differential equations, which is why even today mathematicians are interested in this particular system of equations. In words, we say matter tells space-time how to curve, and in return, space-time tells matter how to move. Any relativistic theory of gravitation, like general relativity, must be consistent with the principle of special relativity, so the effect of gravity cannot be transmitted faster than light. Hence, if the gravitational field of an object changes, the changes propagate through space and take a finite time to reach other objects. This leads to the possibility of gravitational waves from Einstein's equations, just as we have electromagnetic waves from Maxwell's equation. So we can say that gravitational waves are oscillations of the gravitational field. Physically, gravity manifests as a tidal effect. So gravitational waves are oscillating tidal gravitational fields which propagate out from the source. If you look at the equations for gravitational waves in general relativity, the tidal force field is oriented either like a plus or like a cross. Hence, if gravitational wave is incident normally on a ring of particles, it would be tidally stretched and squeezed in an oscillatory, time-dependent manner. So to detect gravitational waves, we must measure the amount of squeeze, or what we call the gravity wave strain. What is the gravity wave strain? If two test particles are initially separated by a distance L, and if a gravity wave signal passes through, changing the separation by delta L, let's take the ratio of delta L by L. Now from this it is clear that for a fixed strain, that means for a fixed H, bigger the device, that means bigger the L, bigger will be the displacement or the delta L. That is why we try to build detectors which are as big as we can afford to build. Gravitational waves were predicted by Einstein in 1916 as an important consequence of relativity using what we call linearized gravity. He gave what we call as the quadrupole formula in 1918, which says that the gravitational wave falls off as 1 by r, is proportional to the gravitational constant g, inversely proportional to c to the power of 4, and to the second time derivative of the quadrupole moment. Since gravitational perturbations determine the metric and hence the spatial separations and time intervals, hence it determines the strain which a system will face when a gravity wave falls on it. So if you take this formula and apply it to a system of mass m moving with a velocity v at a distance r, you get a very simple combination which is shown here. And if you apply this formula to a physical system made up of two trucks weighing a ton each, separated by a couple of meters, rotating at about a kilohertz, the value of h comes out to be 10 raised to minus 39. Looking at this number, Einstein had observed it must have a practically vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. And as usual, he was right, because it took 100 years almost to detect the gravitational waves. Now, though Einstein predicted gravitational waves in 1918, there was for the first 50 years, there was a lot of confusion, because the question people asked was, are gravitational waves physical? Do they really transfer energy, or are they merely an illusion because you're choosing wavy coordinates? It's a wave effect, coordinate effect rather than a physical effect. So it took almost 40 to 50 years for a conceptual framework to determine without ambiguity if gravitational waves exist in general relativity and what properties they have. The physicality of gravitational waves was resolved in this famous meeting of Chapel Hill in 1957 in the discussions of Pirani, Bondi, and Feynman, who showed that the tidal effect of gravitational waves is unambiguous. Once this was understood, the treatment of gravitational waves in the full nonlinear general relativity became a subject of investigation by Bondi and Chandrasekhar. Even though we have the physicality established, even today we don't have a confirmation a la Hertz. And if you ask why, the reason is connected to two fundamental differences between electromagnetism and gravitation. The first is the weakness of the gravitational interaction relative to electromagnetism by a factor of 10 raised to 39, and the fact that unlike electromagnetism, where there is dipole radiation, in general relativity, there is no dipole radiation, but it begins with the quadrupole radiation. So because of this, there is low efficiency for converting mechanical energy to gravitational radiation, except when you have strong fields and objects are moving at relativistic velocities. And the effect of gravitational waves on any potential detector are also very feeble. So the likely sources are not laboratory sources, but signals produced by astrophysical systems where there are huge masses accelerating very strongly. The first person to build detectors for gravitational waves was Joe Weber, who built what we call as the bar detector. This is a resonant bar. So if a gravitational wave falls on it, it will put it into resonance. Now, this kind of detectors are narrowband, and the kind of sources Weber was looking for were violent events like the supernovae. It took another 50 years before the detection of gravitational waves happened, and this required two major changes. One thing was the resonant bars were replaced by laser interferometers, which are more sensitive to measuring displacements. These detectors are broadband, and as I will show you, this plays an important role because the kind of sources we are looking for are not supernovae but coalescing compact binaries. An important watershed event in this particular subject was the discovery of a dumbbell in the heaven made up of two neutron stars. In 1974, the binary pulsar 1913 plus 16 was discovered when Hulse, who was a graduate student like some of you, and Taylor, his advisor, looked for pulsars by the method of radio astronomy called pulsar timing. The discovery of this object was watershed because it demonstrated that gravitational waves are physical, they are accurately described by Einstein's general theory of relativity, and coalescing compact neutron star binaries could be the prototypical sources for laser interferometer gravitational wave detectors. So, when you look at a system like the binary pulsar, you realize that by qualitative arguments, you can argue that the signal from a compact binary increases in frequency and amplitude during the inspiral until it plunges at what we call as the innermost stable circular orbit. Now, this is just ordinary Newton's laws. A system is going around in one system going around the other. It is losing energy, so it will start falling inwards. Now, that is what is called as the inspiral part. And then it reaches a particular point where there are no stable circular orbits, so it just sort of plunges. And it is very interesting that exactly when this binary pulsar like system is sort of going to coalesce, it becomes a suitable source for a laser interferometer gravitational wave detector. So, if you look at the problem, now we have said that we have a technique, we have a source, but still, even though you have these strong sources, the strains are very feeble. Because if you make a simple calculation of a binary neutron star made up of two solar masses moving close to the velocity of light. In the nearest cluster of galaxies, which is the Virgo cluster, the age comes out to be 10 raised to minus 21. So you can see here that from 10 raised to minus 39, which Einstein had, we have gained almost 20 orders of magnitude because we are looking at this astrophysical source. If you can build an interferometer which is a kilometer long, the displacement it will undergo is 10 raised to minus 18 meters. So the fringe pattern is affected by this very small displacement, which is smaller than the nuclear dimension. It's almost like 1,000th of the Fermi. And therefore, if you want to detect gravitational waves, you really have to measure this very small displacement. If you really look at the people doing laser interferometry, you can hit this experiment by all techniques which they know. For example, you use what is called as a power recycled, signal recycled Michelson interferometer with Fabry-Perot arm cavities. By using these kind of techniques, one can sort of say that the laser interferometer is acting like a transducer. It's converting the gravity wave to a photocurrent, which is proportional to the strain amplitude. Now remember, you have to measure something which is 1,000th of a Fermi. And if you ask what is the sensitivity of the Michelson-Morley experiment by which the special relativity we learn in our graduate course, it measured a displacement of about a nanometer. So you can see here that compared to the Michelson-Morley experiment, you have to gain almost 10 orders of magnitude. And assuming that every 10 years you can gain a factor of 10, obviously it would take about 100 years to get to the sensitivity required, and that is exactly what happened. There's another factor of 10 raised to 10 which you have to sort of overcome because your interferometer is sitting on the Earth and it is therefore subject to seismic motion. The order of the seismic motion is of a nanometer. So unless you reduce the seismic vibration by a factor of 10 raised to 10, you cannot measure 1,000th of a Fermi. So there are these twin factors of 10 raised to 10 which you have to overcome experimentally to detect gravitational waves. Even if you can do that, you realize that if you really take a binary neutron star system, if you look at the waveform, it is not a strong wave. It's a wave which is a signal which is very weak. The noise on the detector is very large. So what is shown here in blue is the signal, and what is shown in pink is the noise. So if you really want to detect gravitational waves, you have to use engineering techniques like match filtering, both to detect the signal and to estimate the parameters of this particular signal. So what you do in match filtering is to correlate the known signal with the noisy data. And that is shown in this particular cartoon where you really look at the correlation. Now here your signal matches with the template which you are using and you pick up a correlation. So match filtering really looks for the correlation between a known waveform and the data. And therefore, if you want to detect gravitational waves, you really have to construct this template bank which you have to talk about. Since you don't know the parameters of this particular source, you really have to construct what you call as a template bank. You have to create waveforms for all possible parameters which that waveform may have. Therefore, if you really want to succeed in match filtering, you really have to calculate the signal using general theory of relativity as accurately as sort of possible. So your theory has to be very good, and Einstein's theory turns out to be a very good theory which can be used to calculate these waveforms. And this is the kind of activity which my group and RRI worked on with my collaborators in France, Luc Blanchet and Thibaut Damour. Now, once you have detected this particular signal, you want to find out the parameters of this particular signal. Now, the waveform depends on 15 parameters: the mass of the system, the angular momentum of the system, the distance to the source, the location in the sky, the relative location of the source and the detector when the system coalesces, and what is the phase at coalescence. So since the parameter 15 parameter things are there, you really have to use Bayesian inference technique. So for example, what you do here is, in blue is the signal, and this is the template which you use. You start first, changing the distance, then you change the mass and try to match what is the blue, the signal, the data which you are receiving with the model which you are trying to fit. By doing this Bayesian kind of inference, you can determine what the parameters of this particular source are. What are the masses? What are the spins? How far it is? Where is it in the sky? And how is it oriented relative to your detector? So this is what you basically do. But the important point one has to keep in mind is, if you look at a gravity wave detector, its antenna pattern is all over the sky. So therefore, if you only have a single detector, you cannot do astronomy. So what you really need to do is build a system of detectors, and that helps you to do two things. The LIGO detector, for example, has one detector in Livingston and another in Hanford. They are as far away in the US as possible. You put them here, and the noise in the detector, then the noise in the detector at the other place will not be the same. So you can reject the environmental disturbances by comparing the detector here, the signal detector here. Now, if you have a third detector in Europe, like the Virgo detector, then you can do triangulation, like the police do when they have to find out where a mobile signal is coming from. And by using triangulation, you are basically trying to measure the time delays between the receipt of the signal from different sites. And therefore, you require a global network of gravity wave detectors. So if you really look at the detectors which the LIGO people built, then you basically realize that if you have these detectors, if you really look at a source coming from different parts of the sky, in this part of the sky, the localization is not very good. Now, if you really took the detector in Hanford and moved it to India, for example, just because it's at a distance further away from the other three detectors, you find that the sky localization is good all over the sky. So the important point is, the inclusion of LIGO India would improve the angular resolution on an average by 4 times, and in some directions by a factor of 10 or 20. And it was this scientific case which led to the formation of the Indigo Consortium in 2009. Our plan was to extend the Indian research, which was on source modeling at RRI and on gravity wave data analysis under my distinguished colleague Sanjeev Durandar at IUCA, to experimental activity, to have a pan-Indian gravity wave experiment and participate in the LIGO scientific collaboration. So this led to the LIGO India proposal in 2011 and to the participation in the LIGO scientific collaboration in 2011. Now, if you examine Einstein's equations for gravitational waves and Einstein's equation, you can discover the properties of these gravitational waves. You discover that the gravitational waves travel at the speed of light. They are transverse and not longitudinal, and they have two states of polarization because you have two tidal kind of fields, and they are called the pluses and the cross polarization. As I told you, there are no monopole or dipole radiation because of fundamental reasons. Because you have conservation of energy, linear and angular momentum, monopole and dipole radiation is not possible. The leading radiation is quadrupolar. Just like electromagnetic waves, gravitational waves also take away energy, angular momentum, and linear momentum from the system. And the important point is, just as accelerated charges produce electromagnetic waves, accelerated masses produce gravitational waves. But there are differences. Because of the weak coupling of gravitational waves to the matter, the gravitational waves will propagate unperturbed through space because they interact very weakly with matter. Remember, electromagnetic fields interact strongly with matter. So you can observe gravitational waves from the inside of a supernova or from a point in the Big Bang closer to the Big Bang. If you really are looking for the cosmic microwave background radiation, you are measuring it when the universe was about 100,000 years old. If you can look at the neutrinos from the early universe, it's like looking at the universe when it's 1 second old. But if you can look for gravitational waves from the Big Bang, you can almost see as close to the Planck time, and therefore you can look at the universe as early as possible if you can get gravitational waves from there. The last point I want to emphasize is the properties of gravitational waves, which I mentioned, come from specific theories of gravity. So if the theory of gravity is different, the properties of the gravitational waves will be different. So it could, for example, not be only transverse, it may be longitudinal, it may transfer at speed different than the speed of light, and so on. So because of this, you can finally test Einstein's general theory of relativity if you can measure the properties of these gravitational waves. The last point I want to sort of measure is we can look for gravitational waves from black holes, which are in binary systems. Because black holes are almost like point particles, when you calculate the waveform, it almost is structureless. And all physical effects of the system, like whether it has spin, whether there is backscatter, whether the horizon absorbs the radiation, and so on, all this will affect the waveform which you will see. So it is like measuring it's like having an ECG of the black hole when you measure the waveform observed by your detector. When the system plunges and coalesces, it is like a bell being hit. And this is what is called as the ring down radiation, which was first predicted by our own Vishweshwara many years back. So when you have a black hole coalescing, you can see it's in spiral, then it plunges and merges, and then it rings down. And you can say something about the form of the ring down because that is specific to the theory of gravity which you have. What happens if you, instead of a binary black hole, you have a binary neutron star? Now, a neutron star is not as rigid as a black hole. Depending on its equation of state, it will be either soft or hard. And therefore, though when the system is very far away, it will look like a point particle, as the system comes close by, you will find deviations from the point particle approximation because of tidal interactions. And this tidal deformation, which you can see in the waveform, will be relating to the equation of state which the neutron star should satisfy. So from an astrophysical observation, you can say something about the fundamental nature of neutron interactions, and you can extract out fundamental physics from an astrophysical observation. Now, when I keep saying neutron star and black hole, we have to keep in mind that if you use the general theory of relativity, you can show that the neutron star masses cannot be more than 3 solar masses. So you distinguish between a neutron star and a black hole by the mass which you have for that particular system. As long as the mass is less than the 3 solar masses, we categorize them as neutron star. If it is more than 3, we count them as black holes. So between 3 solar masses and 5 solar masses, there is supposed to be a kind of gap. We really think that the black hole masses should be more than 5, neutron star masses should be less than 3. As of now, people believed that there was a mass gap between these two. Now, gravity wave observations will tell us whether this is really true or whether in the gap also you can have black holes. So this essentially finishes my primer. This is, when you look at the gravitational wave papers, what I told you is the basic thing you will need. to understand those particular papers. Now I come to the discoveries and breakthroughs which really happened in the subject. The first observational run involved only the LIGO detectors. The second observational run included the LIGO detectors and the Virgo detector. It's important to acknowledge the National Science Foundation, which funds the LIGO Observatory and sort of is the LIGO scientific collaboration which exists around this system, of which we are one of the groups. There are many groups all over the world, and the LIGO India Scientific Collaboration is one more group which can use the data which comes out of the LIGO detectors. The first observational run of LIGO began on September 12th, and just a couple of days afterwards, a signal was detected both at the Hanford detector and the LIGO detector. The signals looked very similar. There was a slight time delay of about 7 milliseconds between them. So if you moved the signal and shifted it by 7 milliseconds, they essentially match with each other. So you suspect that you are seeing an astrophysical signal because two detectors very far away are seeing the same kind of signal. Since you can extract out the parameters of the signal by the method I told you, you can take those parameters, use Einstein's equations by using numerical relativity, and reconstruct what the waveform should look like. That is what is shown in the second panel here. And as I said, the signal was very strong. So if you look in time and you could look at the frequency of the radiation, you find that suddenly the signal shows up in one detector, and roughly at the same time, the signal also shows up. So this is called the burst way of detecting radiation. So essentially the signal was so strong that we really didn't need to do mass filtering. You could see it barely directly in the time frequency. The signal to noise was very high. It was about 24. And this was the first direct detection of gravitational waves. The system it corresponded to was a system of 36 and 29 solar masses, and the distance was estimated to be about 410 megaparsec. Now, the important point you have to keep in mind, this was not just about the first detection of gravitational waves. It was the detection of a binary black hole that merges within the age of the universe, because you are seeing that detection. It is the first observation of a stellar mass black hole whose mass is more than 25 solar masses. People had seen black holes in the X-ray band, but all those masses were much smaller, something of the order of 15 solar masses or something like that. So again, you are looking at a new class of objects which was not seen by electromagnetic observation. Now, when you know the mass of a particular object, it tells you something about the environment in which this object is basically formed. So obviously, if you want to form a very massive object, it should not lose mass. So it tells you something astrophysical, that the stellar winds are very weak. And if the stellar winds have to be weak, it tells you something about the metallicity of the medium, that it has to have low metallicity. So you can see here that detailed astrophysical information can be extracted just from the mass of this particular system, which we are basically seeing. And as I told you, the gravity wave is coming from a binary black hole system, which is at a cosmological distance, which is about 410 megaparsec. And as I told you, once you have a signal, you can test the general theory of relativity, and you can test it in a regime where the gravitational fields are very strong, because when the system is merging, the two systems are very close to each other. So the gravitational field have to be very, very strong when that happens. So the discovery paper, which came out on 11th February 2016, had 37 authors from the Indian institution and citations to seminal papers, including Indian researchers. This included the papers which I wrote with my French colleagues, the papers by Vishweshwara, the papers by Durante's group in Ayuka and so on. And it's very interesting that this event, which happened billions of years ago, allowed the approval of LIGO India. It was 1 week after the detection, the LIGO India in principle approval was granted by the government, and the institutes involved in setting up LIGO India are the RR-CAT at Indore, IPR at Gandhinagar, Ayuka at Pune, and DCSCM, which is a cell of the DAE, which does civil in construction and so on. For this discovery, the 2017 Nobel Prize in Physics was given to the people who were leaders in this particular subject. There was Ray Weiss, who was the experimenter, got the half the Nobel Prize, and a quarter of the Nobel Prize was shared by Kip Thorne and Barry Barish. And the citation basically said, for decisive contributions to the LIGO detector and for the observation of gravitational waves. It's important to keep in mind that it's a great experimental achievement, which is why the half the Nobel Prize goes there. But it also required understanding of the theory, which is what sort of Kip Thorne was involved in. And in addition, you really needed to put together something which went beyond lab physics. You really needed to set up a large consortium of people so that different aspects could be explored at the same time. So there were about almost 1,000, a little more than 1,000 people involved in the LIGO scientific studies, and this was the active, realization which was brought in by Barry Barish, who was a particle physics. And in particle physics, we know that this is the way the research is basically done. The second observational run began on 30th November 2016, and towards the end, on 1st August, the Virgo detector became sensitive enough to join the search.
Recording in progress.
So the Virgo joined on 1st August 2017, and just a fortnight later, we had the first discovery of a gravitational wave from a binary black hole, which was seen both by LIGO and the Virgo. So LIGO Hanford, LIGO Livingston, and in Virgo, which was not as sensitive, you had the signal which was seen with a small signal to noise ratio. But the important part, as I told you, is the relevance for sky localization. If you had only the LIGO detectors, the sky localization would be about 1,000 square degrees. Because you had the signal also in the Virgo detector, the sky localization became 60 square degrees. And therefore, if you want to look for follow-up, this really is very, very crucial. And this was indeed the case, because on October 3, the Nobel Prize was announced. But on October 16, the collaboration announced a discovery which was even more spectacular, because it detected the gravitational wave not from a binary black hole, but from a binary neutron star. So what is shown here is something which is happening in the LIGO detector, but at the same time, in the Fermi detector, again a signal is sort of seen. So you can see here that the gravity wave detector is there. There is a plunge which happens, and almost at the same time when the plunge is occurring, the gamma ray detector Fermi is seeing a signal. Now remember, this could just be an accident. So the important point is to really see, are we really seeing the signal in the electromagnetic band, gamma ray band by Fermi and LIGO? Is it from the same astrophysical source or from a different? Is it just an accident? So for that, it was important to really find out the localization, and therefore, because of the fact that the three detectors were online, the sky localization was about 28 square degrees. Now, because it was such a small, an alert was informed to our collaborative people in electromagnetic with whom we had MOU, and immediately by the night they had sort of discovered an optical signal from the same thing. So you have a signal from the gravity wave in gamma rays and what is called as a kilonova. 82107 is a kilonova. So you can see that because of the fact that you can localize the source very well, you can do follow-ups and try to find out the electromagnetic counterpart of this gravity wave source. So again, many firsts. The first observation of gravitational waves from a neutron star system. First observation of gravitational waves and electromagnetic waves from a single source. It supports the hypothesis that the source was produced by the merger of two neutron stars in a particular galaxy, very specific you can identify. It was followed by a short gamma ray burst and a kilonova, which is usually powered by the radioactive decay of R process nuclei, which are synthesized in the executor. So you can see here, such amount of astrophysical details we are being able to sort of find out. From the observations, we can say that the reactions which are happening are correspond to R processes, which we know from nuclear physics. And as I told you, because it's a neutron star, there will be a tidal deformation. So from the observations, we can put some limits on how much tidal deformation is there in this particular system. And that helps us rule out some equations of state, not necessarily all of them. It's important that one has to realize that we take the presence of gold and platinum and uranium and so on as natural. But how does it get produced in the universe? Now, the neutron star merges are the best places for producing these kinds of elements because of the fact that there are R process, there are a large number of neutrons which are there from these neutrons are mergers, and only by using supernova you cannot produce the amount of abundance which you see of gold and platinum in the universe. This object became so famous that if you do a Google search, there are more than 2000 papers on this particular object, which deal with the observation, the interpretation of the observations, the models to explain the observations, and so on. So we are finally there in this era where we can do multi-messenger time domain astronomy, and therefore we are in an era where we can have collaborative gravitational wave, electromagnetic, and neutrino observation. Because of the fact that you can measure the distance and you can measure the electromagnetic counterpart, so you can measure the redshift, you can measure the Hubble constant. So you can measure the cosmological constant, and do cosmology by this particular object. And the other important point is that, as I told you, you can test general theory of relativity in many, many ways. So using the gravity wave observation, limits were put to various aspects of the general relativistic effects which happen, and you can see all the details in a physical review letter with the collaboration wrote. So with the end of the two observations, what happened? If you look at what we knew from electromagnetic observations, we basically had neutron stars from pulsars. So these are the electromagnetic neutron stars which were known. These were the electromagnetic black holes from X-ray observation. As you can see here, their masses are around the order of about 15 solar masses. The observations of gravity waves from the first two observational runs essentially showed us there are black holes which are more massive, so they are a different population compared to the electromagnetic black holes. And the electromagnetic neutron stars are not as many as here, but as the observations go on, we will be able to see more and more neutron stars by gravity wave observation. So Then once that happened, the third observational run began. And in that, we started doing the following. The moment we saw a gravitational wave event, we sent out, and we were sure that it was a gravity wave event. We informed the astronomy community that, hey, there is a gravity wave signal in this particular part of the sky. If you want, you look for an electromagnetic radiation from this part of this particular sky. So this is basically called low latency alerts. And you can see that almost within a few minutes, we send our information. So all the gravity wave processing is rapidly done very quickly so that the electromagnetic observers can event. So at the end of the third observational run, we had 90 gravity wave events. So you can see here, more and more black holes are being sort of seen, and the picture is getting more and more sort of filled. The important point you have to keep in mind is that we saw the second binary neutron star during this run. We saw a neutron star black hole system, a couple of them during this particular run. We saw an intermediate mass black hole. That means a black hole more massive than 100 solar masses in this particular observational run. And of course, different varieties of observations by which different astrophysics can really be extracted out from this particular thing. So you can see here, the third observation run essentially consolidated our picture of the So because we have a population of objects, we can put estimates how many binary black holes should be there to coalesce per year per gigaparsec cube. So these numbers can be sort of extracted out. How many binary black holes you can find, how many binary neutron stars, how many neutron star black holes can sort of predicted from our model calculations. And as we go to the next level of observations, we can basically do the following things almost in a standard way. So the third run gravity wave data, as I told you, allowed us to do many different things. I'll send alerts, identify exceptional events, create a catalog, infer the rates, test general relativity, do cosmology, look for gravity wave lensing. Are two sources independent sources, or are they just lens events of the same thing? And of course, not only we look for transient sources, we look for gravitational waves from supernova, which we call burst sources, gravitational waves from neutron stars, which we call persistent sources, and maybe there are exotica which put out gravitational waves like cosmic strings, and we look for them also. So with that, we have come to today, where currently the fourth observational run is happening. We are able to send out alerts even more rapidly now. And now we send out alerts not only for significant events, but also for insignificant events. When the signal to noise ratio is small, they have low significance, but we send out an alert because some astronomers think that maybe there may be an astronomical counterpart associated with them. I mentioned that in this particular run, we discovered an interesting object called 23529. I had mentioned to you that in the region between 3 and 5 solar masses, there is supposed to be no binary black hole. Now, this object has a mass which lies in that particular black hole. So it looks like maybe the lower mass gap really doesn't exist, and maybe black hole masses may be smaller than 5 solar masses. So you can see here that whatever we used to believe is getting overthrown just by the gravity wave observation. And what I show here is that I have told you all the short duration sources which exist here. But as I told you, there are long duration sources, there are burst sources, and maybe you can't look at individual sources, but there can be a stochastic background because we can't identify single sources, they create a kind of stochastic background and we look for them also. With this, we come to the last part of my talk. We are currently in the fourth observation run. The fifth observational run is sort of being planned. It will happen 2 or 3 years from now. In that particular point, instead of having a few events, an event in few days, we'll have almost 3 events per day. Because your detector is becoming more sensitive, it can look further away and therefore you can see more events per day. Now, all this has an impact also on LIGO India because in the intermediate, as I told you, our in-principle approval came in 2015. After that, we have found a site at the place called Aunda. Our colleagues in our IPR have done some prototyping for the vacuum system. At the RRCAT, we have built a facility so that we can build a prototype interferometer. At Ayuka, computing infrastructure has been set up. The HRD for the project is being identified and so on. In 2019, Indigo became what we call today as the LIGO India Scientific Collaboration. And on April 17, 2023, the full approval of LIGO India of about 2,600 crores was sort of sanctioned. We expect LIGO India to come online in 2030. This date will definitely probably slip, but the important point is that people who study the relevance of the LIGO India detector in the next generation detector, we basically realize that even beyond O5, the fact that LIGO India exists will be very relevant for multi-messenger astronomy. Just as we have, in addition to optical radiation, X-ray, gamma ray, infrared radiation, gravitational waves also occur not only in the millisecond range, but in the minutes range, years, or billions of range. But they cannot be seen by detectors on the ground. You need detectors in space, which is the LISA detector, or you use pulse timing array, or specialized detectors like the Big Bang observer. So once you have these different detectors, you will be able to do multi-band gravitational wave astronomy. And that is really what we look forward to in the next few years. In 2023, the pulsar timing people announced that there is strong evidence for gravitational waves in the nanohertz band, this band. And these are gravitational waves which cannot come from ordinary black holes, but they come from supermassive black hole binary. So therefore, the stochastic background of these particular objects is what we are seeing in the nanohertz band. The LISA mission was adopted formally in 2024. The construction will begin in this January and is supposed to be launched in 2035. So you can see here that this is not just the beginning, but this is something which is just opening up a new window to the universe. When you build together the third generation detectors, which are called Cosmic Explorer in the US, Einstein Telescope in the Europe, you will be able to find all the coalescing binary mergers in the visible universe. Till the end of the edge of the universe, all the neutron stars will be seen, all the black holes will be seen. And as I told you, there is a different band of gravitational wave frequencies which will be seen, which will explore different astrophysical objects. So from known knowns and known unknowns, eventually we will work towards the unknown unknowns, as somebody would say. So to conclude, the next generation gravitational wave network will have a transformative impact on the emerging field of gravitational wave physics and astronomy, which will lead to an era of precision gravitational waves and multi-messenger astrophysics. There is a tremendous discovery potential in cutting edge research because you will probe black hole formation, evolutions to the beginnings of star and galaxy formation, and potentially to the early moments of the universe. it will enable profound quantitative probes of QCD, as I told you, because of the binary neutron star case, neutron-rich matter, Hubble tension, which is a big problem, it will throw light in cosmology. And because we can look for dark matter and dark energy in our observations, it will say something about the new physics which exists. So the scientific impact goes beyond gravitational wave astrophysics. It touches fundamental physics, particle physics, nuclear physics. The sensitivity which we hope to have, 10 times more than the sensitivity which we have today, will lead to major technology advances, advanced electronics, material science, quantum sensing, quantum information science, and so on. So essentially, it touches everything. As somebody said, every technology they are touching, they are pushing, and there are a lot of technologies they are touching. So therefore, the faint strains, very, very weak strains of gravitational wave symphony, they are really a whisper to the new revolution. So to the young people in the audience, I would just say, come decipher the universe by using gravitational wave observations and multi-messenger astronomy. Each one of these things is something which is waiting to be sort of observed. With that, I thank you for your attention and apologies for spilling over to a few extra time.
No worry at all. Thank you very much, Professor Bala, for a very exciting and very informative talk. Now the floor is open for a few questions. Anyone would like to ask a question, you may raise your hand. I see two hands already. Professor Buddhaswamy, you want to ask a question? Go ahead. Buddhaswamy. Buddhaswamy, you can unmute yourself and ask.
Very,
Yeah.
very nice informative talks on navigation. Sir. Thank you very much. I have a couple of questions. In which country LIGO and barcode detectors are located? As far as the funding is concerned, what is the contribution made by India towards these detectors? What are the practical problems facing in detecting the graviton? These three questions, these are my
President, I
questions.
can't hear the question clearly. Can you
Hold on.
repeat them?
Sir, can I once again?
I
Yeah,
could not hear him at all.
Oh,
Okay.
I see.
Ask your question. Okay, let's see. Ask your question. Again, slowly.
Sir, which country LIGO and barcode detectors are located? No, not hearing at all?
He wants to know where they're located. That's what you want?
Yes, yes.
Where the LIGO detector is located. LIGO India is located. He wants to know.
Yeah, so the LIGO India detector is in a place called Hingoli in Maharashtra. It's close to Nanded.
Okay.
So the site has been acquired, and now, the civil construction will start in a few months.
Okay.
Okay, now, Professor Dayananda, you want to ask question? You can unmute yourself. Dayananda. Dayananda, you may go ahead and ask your question. Unmute yourself. Okay, in the meantime, I have a few questions. What kind of signals can we expect from gravitational waves from the very early universe, or when the inflation was taking place, or when the dark matter was beginning to be formed? Can you give some idea about that?
Yeah, so as I said, the signals from the very early universe are very sensitive to the models which people have about the inflation model which they will basically use. So the way people will look for it is look for the stochastic background which a particular model will sort of predict.
Yeah.
Now, it turns out that the frequency, even the space detector, will not be sensitive to the specific gravitational wave detector signals from these particular things. So, it is a very sensitive model, sensitive prediction, which you really will really have. So, currently, for example, in the LIGO, what we really do is we look for stochastic signals with a particular frequency sort of fall off and say that our data is consistent with this much level of
Yes, yes.
signal with that particular frequency behavior. And
Yes.
similarly for dark energy and dark,
Matter.
so depending on the model which you use for the dark energy and the dark matter, the prediction of your astrophysical signal will change, and therefore the consistency of our data with that value of the parameter is what we can sort of put a statement on.
Okay. I'm quite amazed at the level of accuracy which we can measure distance 10 to power of minus 18 meters.
Yes.
What kind of a technology can it be there? No, can you throw some light on that? 10 to
No,
power
as I basically said, you begin with the Michelson interferometer, then you have a Fabry-Pérot cavity so that you bounce it about 150 times. So it's like artificially creating a detector which is 150 times 4 kilometers, so 60 kilometers. Then you basically do power recycling. So when the power is increased, again at the high frequency, it improves the sensitivity by a certain factor. And then to tune the signal, you basically use signal recycling. Then you basically also build special photodiodes, very large photodiodes, which allows you to measure very small photocurrent. So all these things put together allow you to do this particular measurement of this very small photocurrent, which this signal, which you can measure with.
Dr. Dayananda, you can unmute yourself.
Yeah. Good afternoon. There's a lot of noise. I'm sorry about that. Yeah, it was a very nice talk, Professor Bala Iyer.
Thank you.
My question is regarding the graviton.
Yes.
What is the status on the research of the graviton? Thank you.
Yeah. So as I said, in this particular, whatever I've been talking about, everything is based on the classical understanding of gravity, which is general theory of relativity. And therefore, at this particular point, directly, we don't say much about the quantum theory of gravity. But as I told you, when we start making measurement of the properties of gravitational waves, at that particular, for example, we have been able to put some limit because electromagnetic radiation and gravitational wave radiation is coming from the same source. So we can put a limit on the speed of gravitational waves relative to the speed of light. Now that is almost close to each other. But eventually imagine that you have a source which is so far away that we can find a little deviation from the speed of light. Then it would definitely tell you that just like neutrinos have small mass, maybe the graviton has a small mass. So therefore, Einstein's theory of a massless spin 2 graviton is not correct. You really should look for a theory where there is a massive graviton. So when we start measuring the properties of gravitational waves, eventually we will be able to say something about the graviton or the quantum nature of the theory, which is consistent with the observation.
Thank you, sir.
Any other
Uh,
Any other questions?
yes, sir, I have a question.
Okay,
Yes.
please ask.
Yeah, you
Sir,
mentioned that
uh,
neutrons are
Wait, one by one, please. One by one.
shall I ask, sir? Or shall
Trikanta, you can ask. Okay.
no, sir. Sir, good afternoon, sir.
Yes.
I have two questions in principle, actually. Um, one is you said the properties of gravitational waves can be different in different theories of gravity.
Yes.
I didn't understand because I always feel that any wave, should have whatever be the theory, it should have the same properties like light property or electromagnetic
No,
waves.
because just to the property of the wave comes from the property of the interaction which you talk about. So, for example, if gravity is not transmitted by a massless graviton but by a massive graviton, the Lagrangian of that particular theory will have an extra mass term. So therefore, that is what is meant by different theories of gravity.
It depends on the
The
graviton.
Lagrangian which you use for the theory. So depending on the theory, depending on the interactions which are put in the theory, the properties of the gravitational wave will derive from that Lagrangian which you have for that theory. And therefore, the property of the gravity wave will be different. So, for example, there are theories where the gravitational wave is not only transverse, but it also has longitudinal modes. There are theories where the gravitational wave speed is not the speed of light, but different from the speed of light.
Sir, one more thing. When we say that the gravitational waves are transverse,
Yes,
and also we say it travels with the speed of light,
yes,
it has been confirmed with experiments, or you have taken part? I mean,
yes.
we assume that it
So,
is
as I
like.
said, the data, we will be able to put limits on how much it is the speed of light close to the, so the data will, it will always be up to a certain level of accuracy. So we know, for example, the gravitational wave travel at the speed of light up to the level of 10 raised to minus 15 or 10 raised to minus 16. As the observations become more accurate, that level will become even higher. So it will eventually approach the speed of light with, as close to the speed of light as possible.
Professor Nagaraj, you want to ask question?
Thank you, sir. Thank you.
Professor Nagaraj, Professor Nagaraj, you can ask your question or comments.
I have one question, sir.
Wait, sir, wait, Professor.
Okay.
Please wait. Wait, you have already asked question. Please wait for others. Nagaraj, Nagaraj. Why?
Yes,
Nagaraj.
sir. You mentioned that neutron stars mergers produce gold, platinum, and uranium.
Right.
I just want to know what may be the frequency of merging of these neutron stars. Any
So the
idea?
merger comes in the kilohertz range. So the neutron star, depending on the mass of the system, you can predict when it is supposed to collapse into beyond the last stable circular orbit. For the neutron star, it turns out that the frequency of the gravitational wave at the merger is of the order of kilohertz.
Oh.
The gravitational wave radiation is of the order of kilohertz. But then, as I told you, the statement about the elements like gold, etc., come from the observations of the kilonova. It turns out that you can observe the electromagnetic counterpart, and they have radiation in the infrared, optical, and so on. And it is those electromagnetic observations which tell you something about the abundance of these R process nuclei. Because depending on the composition, the color of those electromagnetic radiation sort of varies. So it is a detailed function of the nuclear physics which happens when the kilonova goes off.
So, Rudraswamy, you want to ask a question?
Sir, one more question. In continuation of what Nagaraj said, I was asked. Can I ask, sir?
Yes,
go on.
Sir, neutron stars, as we understand, it's mostly consists of neutrons, right?
Correct.
But when we get this gold, platinum, etc., we should also have protons there.
Correct.
So you mean during the merger, protons are produced? Or?
No, so as I said, there are a lot of these neutrons, and essentially because of that, there is a lot of, potential for R process to take place. And it is that R process which produces these this gold, silver, and uranium, and so on. So whatever nuclear
protons
physics.
also are produced, right?
Yes, certainly. So many particles are produced at the same time.
Yes,
Electrons are also produced. They will be there. Professor Rudraswamy, you want to ask a question? Briefly, please. Rudraswamy. Okay, he's not there. If no further questions are there, I request Professor Nagaraju to propose a vote of thanks. our General Secretary.
Yes, sir. I think there are no other questions. Maybe Rudraswamy has.
Small question, sir.
Yes, sir. He is, I think, trying to ask, sir.
Okay, be quick. Okay.
Okay, as far as thing is concerned, what is the amount of contribution made by you?
I think there is some.
Sorry, sir.
problem
So
with
there's a
this,
problem with the audio. No, we can't hear you. So we can't hear you. So please.
Maybe he can type his chat in his
Yeah.
chat and you can see it.
Yeah.